Hello everyone, welcome to the course Basics of Materials Engineering. Today in this week we'll be studying about phase diagrams, mainly about iron carbide diagram, and also some eutectic reactions, monotactic reaction and other reactions. This course is offered by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras. I'm your TA Alka Jangir from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will be helping you in solving your assignments. Then we'll be reading about some notes, going through some notes which will be helping you in solving your assignments. So first question is the invariant reaction of two solids transforming to a single solid at constant temperature upon heating is known as. So in case of solid state, there will be OIT in last. It will be like eutectoid, peritectoid type of name. So your options are eutectic, eutectoid, peritectic, peritectoid. So here two solids are transforming into a single solid. So upon heating, so this will be your eutectoid type of reaction. So we can explain this by saying when a solid transforms into solid B plus solid C, which also occurs in iron carbon system. So this is your eutectoid type of reaction. So the eutectoid and peritectoid invariant reactions occur for systems in which all of the phases involved are solids. So the eutectoid reaction involve a single solid phase decomposing into two different solid phases, such as gamma converts into alpha plus beta. So the iron carbon system shows this type of reaction, and the peritectoid invariant reaction involves two solids reacting to form a single solid phase. So this will be opposite of your eutectoid reaction, and this type of reaction takes place in copper zinc system, brass system. Now because solid state diffusion is involved in phase change reactions, these processes are slower than those in which a liquid phase is present. Now cooling rates must be reduced to approximate a quasi-static thermodynamic process for these reactions. Second question is monotactic reaction refers to. Your options are a liquid phase transforming to another liquid and solid phase upon cooling. Second is a liquid phase transforming to another liquid and solid phase upon heating. A liquid phase and a solid phase transforming into another solid phase upon cooling, and two liquids transforming to another liquid phase and solid phase upon cooling. So in case of monotactic, your one liquid will convert into another liquid plus solid phase. So this liquid phase transfer upon cooling. So this will be your answer. Now we can explain this by there are 5 invariant reactions where freedom of degree is 0. So first is eutectic, in which your liquid will convert into two solids. Eutectoid, your solid will convert into two different solids. Peritectic, where liquid plus alpha will convert into another solid. And peritectoid will be your opposite of eutectoid. Monotectic will be your liquid converting into solid plus another liquid. This liquid will be different in composition. Now third question, you have to identify correct statement. So first statement is solubility of carbon in plain carbon steel is higher in BCC ferrite since it has more free space compared to FCC austenite. Second is solubility of carbon in plain carbon steel is higher in FCC austenite since it has single largest free volume compared to BCC ferrite. The solubility of carbon in steel has nothing to do with crystal structure, or delta iron is magnetic and has BCC crystal structure. So only one statement is correct here, which is second one. So the FCC or austenite has the highest solubility of carbon because of larger size of your octahedral voids. Now, solubility limit can be defined as the maximum concentration of solute that may be added without the formation of a new phase. And excess addition may result in the formation of another solid solution or compound. Now, the solubility of carbon in plain carbon steel is higher in FCC austenite because of larger void size. And there are two types of interstitial sites, which are octahedral and tetrahedral. And in case of FCC, the former is significantly larger than the latter, whereas in BCC, these are nearly same. So the total open space is shared by more number of sites in BCC. Therefore, interstitial gap in BCC is much smaller than FCC, which leads to higher solubility in austenite. And here, as it's written, delta is magnetic, so delta is not magnetic after Curie temperature. Above this temperature, your steel and iron, this will be non-magnetic. So delta iron is non-magnetic and has BCC crystal structure. Third question is based on iron carbide phase diagram. So in this, the eutectic mixture of austenite and cementite is called. Your options are martensite, ladybirite, bainite or pearlite. So in case of eutectic, it will be ladybirite, and in case of your eutectoid mixture, it will be pearlite. Eutectoid mixture will be of ferrite and cementite. So here answer will be ladybirite. So we can explain this by saying that eutectic mixture of austenite and cementite is called ladybirite, and at temperature 1130 degrees Celsius and carbon composition 4.3%, this reaction takes place where liquid iron converts into your austenite plus cementite, and one liquid here converts into two solids. This point here 4.3 composition, and this temperature, this is your eutectic point. Now fifth question is cementite is, your options are a eutectic mixture of iron and carbon, a eutectoid mixture of iron and carbon, an intermediate compound of iron and carbon, or a eutectoid mixture of austenite and ferrite. So cementite, as you know, at this point, at this line 6.7 weight percent of carbon, this line, vertical line, it corresponds to the intermediate compound that forms and known as Fe3C. So this is your orthorhombic type of crystal structure. So cementite, which is also known as iron carbide, is an iron carbide compound that is extremely hard and brittle. And in white cast iron, cementite is the dominant phase. It forms when carbon in the iron combines with iron atoms to create a hard crystalline structure. Okay, so the presence of the significant amount of cementite is what gives white cast iron its white appearance. Sixth question is the maximum solubility of carbon in iron in solid state is. Your options are 4.13%, 0.78%, 2.14% or 0.022%. So maximum solubility of carbon. So for this you can choose between delta iron, gamma iron and alpha iron. So these all among these three, you know that austenite has the highest solubility. So and its maximum solubility is at the eutectic temperature, which is 2.14. So this will be your answer. The solubility of carbon varies in different forms of iron. In delta iron, the maximum solid solubility of carbon is 0.1%. Here it will be 0.1% at peritectic temperature. And in gamma iron, the maximum solid solubility of carbon is 2.03%. So in case of gamma iron, it is around 2.03 or 2.14 weight%, and austenite is a solid solution of carbon, is in face centered cubic iron, and solute atoms occupy interstitial positions in this lattice. In case of alpha iron, your carbon has limited solid solubility of about 0.008% at room temperature, and it goes maximum at eutectoid temperature, which is around 0.0025%. And the solid solution of carbon in alpha iron is known as ferrite. Seventh question, you have to tell what is the mass fraction of cementite in perlite at eutectoid composition, rounded to the 2 decimal places. So you have to tell what is the fraction of cementite at the eutectoid composition. So this point will be considering, and this is your 100% ferrite, this is your 100% cementite. So this is the tie line for getting the mass fraction. Now from Lever rule, you know how we calculate the weight fraction of particular composition. So I told this in previous class. So for getting cementite content, we'll be taking this part, which is 0.76 minus 0.022 divided by the entire length of the line. So length will be 6.7 divided by 6.7 minus 0.022. Now this will give you mass fraction, which will be 0.11. This will be fraction of your cementite, and if you minus it from 1, that will be your fraction of your ferrite that will be present in this eutectoid composition. Eighth question is the hypereutectoid steels have structure of. Your options are perlite alone, or ferrite and perlite, or cementite and perlite, or ferrite and cementite. So your answer will be phases of cementite and perlite. So in case of hypereutectoid, your steel will have composition higher than eutectoid composition. So it will be having carbon percent higher than 0.76 weight percent. Now, according to iron carbon phase diagram, the composition of steel contains 0.8 weight percent of carbon as eutectoid composition. So, in certain composition where upon cooling austenite to lower than 723 degrees Celsius at eutectoid reaction, the austenite turns into pearlite, which has alternate layers of ferrite and cementite. So here your entire austenite converts into pearlite. So there won't be any pro-eutectoid ferrite or cementite. So in case of hypoeutectoid steel, which will be having lesser than 0.84% carbon, this is given different in different books. So it can be 0.84 or 0.76 weight percent depending on what is the source. So this will be your hypoeutectoid steel, which will be containing proeutectoid ferrite plus pearlite. And in case of hypereutectoid steel, it will be having more than 0.84% of carbon steel, and which will be having pearlite plus proeutectoid cementite. Now in ninth question, you are given the weight of the steel. So in case in a 2.5 kg of austenite containing 0.65 weight percent of carbon cooled below 727 degrees Celsius. This is your eutectoid temperature. The mass of pearlite rounded off to the 2 decimal places is in kg you have to tell. So you first calculate mass fraction, then multiply with this mass of austenite. For mass fraction you have to use lever rule. So as told earlier, we are given what is the carbon composition. So 0.64 will be lying between eutectoid temperature and your 100% ferrite. So here you have 100% ferrite, here you have 100% pearlite. So you have to tell mass of pearlite. So for getting mass of pearlite, for
Hello, ma'am.
yeah,
Actually, this 727 degrees Celsius, will it be varying for different book? I mean, somewhere it's actually given like 725. Do we need to fix it to a one value, 727 or 725?
okay, but this won't change your answer for this carbon composition. But yeah, this is given different in different books. It also depends on whether you are looking at iron carbon diagram. In that case, you'll be getting equilibrium diagram. So that will be having graphite forming. That those lines will be different compared to these lines as well. And as I told earlier, 0.76 is also told 0.8%. It is rounded off in various books, or it is told different in different books. So for particular, so in for example in this question, I had to consider 0.8% to get the answer that was given by professor. So it wasn't, yeah, when I used 0.76, then it was coming around 2.22, which wasn't accepted answer.
Okay, ma'am. And also, will is there any reaction in which we will be getting the cementate will be decomposed?
Cementite will decompose at what temperature? What your
I mean, for the gray cast iron, it was actually they are saying the decomposition of cementate the cementate will be decomposed.
So, are you talking about like why this iron carbide is not a equilibrium diagram? In that case, we consider that if cementite is considered a metastable phase, so it is not stable completely. If you heat it to higher temperature for very long time, then it will break into graphite. So it will convert into graphite and ferrite. So it's metastable phase. That's why this graph, this iron carbide diagram is also metastable diagram, not completely equilibrium diagram. But because it, yeah,
I mean, if we are getting the at 0.76, we will be getting alpha on cooling alpha plus Fe3C, and when we go through till 6.7, we will be getting the same alpha plus Fe3C, isn't it? So, is there any reaction which we get this Fe3C decomposition? I mean, separately.
At which points are you talking? Like eutectic and eutectoid temperatures?
Eutectoid temperature or
Yeah.
any other point.
So after this point, you are asking whether we are cooling further, it's decomposing further. Am I correct?
Yes.
So
Yes, sir. Yes, actually, we will be getting alpha and Fe3C, but is there any reaction which we get Fe3C decomposed as separate?
no, it won't be decomposing. Like after this temperature, your entire alpha is converting into alpha plus Fe3C. So only solubility is changing for your alpha. So solubility is reducing. So from alpha, some carbon will be rejecting and forming into Fe3C. So there will be only alpha plus Fe3C below this temperature. There won't be any decomposition of cementite below this temperature, eutectoid temperature.
Okay, ma'am.
Okay. So in this case, you are told that there is some composition given 0.65%, which is lying between your eutectoid temperature and your here it is your 100% ferrite. Here it is your 100% perlite. So for getting the percentage of perlite, you'll be you'll be taking minus 0.65 minus 0.022 divided by entire length. So divided by this zero point 0.8, this minus 0.022, then you'll be getting mass fraction 0.84. Now this is the mass fraction of your perlite. Now for getting the weight in entire austenite, then you'll be multiplying this with 2.5 kg, then you'll be getting 2.11 kg is your perlite, and remaining, if you minus from 2.5, that remaining will be your pro-eutectoid ferrite. That will be your weight of ferrite. Now next question is the SAE designation of a plain carbon steel given as 1080 can be classified as. So your options are hypereutectoid steel, hypoeutectoid steel, hypereutectic steel and eutectoid steel. So this will be eutectic steel. Now this is how your SAE steel grades are given. So these are 4 digits. So for initial 2 digits, they tell what is the type of steel, what type of alloying is there present, and last 2 digits they tell what is the percentage of carbon. So if it is 0.880, then it will be 0.80 weight percent of carbon, which is an eutectic, so it's hypereutectoid steel. It's incorrect here. So it will be hypereutectoid steel. So for different steels, if it is 10, then it will be plain carbon steel with having 1% of manganese. And in case of when it is 20 or something like that, then it will be nickel steels. It can be nickel chromium steels, it can be molybdenum steels, it can be chromium steels. These will be having very less percent. They are not alloy steels, they are plain carbon steels. Now 11th question is, in a binary system of A and B, a liquid of 20% A is coexisting with a liquid of 70% A. So for an overall composition having 40% A. So your composition of alloy is 40% A. So the fraction of solid is. You have to find out what is the percent of solid. So your options are 0.40, 0.50, 0.60 and 0.75. So answer will be 0.40. So by this question you can assume this type of figure. Now in this figure your X composition is in between this liquidus and solidus, which is lying at 40% of A. Now we'll be taking all these percentage in terms of A only, because your this composition is given as 40, or you can take 100 minus 40 as well. So if it is 40, then your liquid is existing at 20% A. So this is 20% and this is your 70% A. So we'll be taking 70 minus entire length will be in your will be getting 40 minus 20, which will be fraction of solid, divided by entire length, so which will be 70 minus 20. So this will be, your answer will be 0.4. Now that's all from the question. So if you have any query you can ask, or I'll be moving to the notes. Okay, so first we have form of eutectic mixtures in general. So when we talk about eutectic mixture, they might consist of two solid phases. So they can be of form of two pure solids. So there will be pure solids and mixture of those, or it can be between two solid solution as shown in this graph here, this figure here. Your solid solution is forming at the both sides, alpha and beta, then these two will be forming eutectic mixture. They can also be intermediate phase. So if you consider eutectoid phase, then in that case as Fe3C is an intermediate phase, so that can also be there, or combination of intermediate phase and solid solution, they can also exist. Now this is type 3. In previous chapter we studied about type 1, which was isomorphous type of systems, which had this type of graphs, and type 2 was having complete solid solubility, so pure solids were forming eutectic mixture. In this case we'll be having solid solutions forming at the terminals, which will be forming eutectic mixture. Now most metals are partly soluble in solid state, hence this phase diagram is the most common type. Now melting points of two metals are Ta and Tb, and the eutectic point will be very less compared to these two. So these eutectic type of reactions, they are very important in case when we want something easily, which melts easily and also easily manufacturability, so which is used in case of cast irons and solders. So this most metals are partly soluble in solid state, hence this phase diagram is most common type, and melting point of two metals is Ta Tb, and your E point Te will be your eutectic point, and Ta E Tb, this Ta E Tb, this upper line will be your liquidus line, and this downward line TaF G Tb, this will be your solidus line. Now example of this type of phase diagrams is in case of copper silver, lead tin and tin bismuth. In these alloys, single phase areas are, in case of this liquid phase above liquidus, this liquid phase is single phase, and this alpha, beta, these are single phases. And liquid phase above liquidus, partially soluble in solid state, implies that a solid solution must form. Now alloys of this type never solidify pure A or pure B, but a solid solution or a mixture of solid solution. And the areas below the melting point of A and B are single phase alpha and beta solid solutions. Alpha is a solid solution of B in A, and beta is solid solution of B in uh, beta is solid solution of A in B. These solid solution are also called terminal solid solution. Terminal are uh, at the end of these phase diagram. So now two phase areas. Now this liquid plus alpha, liquid plus beta, and alpha plus beta, these are two phase areas. At TE, your solid solution alpha dissolves a maximum of this TE, the point F, it dissolves 20% of B, and similarly in this side at this beta, it dissolves maximum of 10% of A as shown by point G. This is your maximum solid solubility. Now with decrease in temperature, the maximum amount of solute that can dissolve decreases, which and FH and GJ are called solvers lines. So FH, this line is solvers line. As the solubility is keep on increasing with increasing temperature, this is your solubility line. And this is called solvers line, and it indicates maximum solubility for saturated solution of B in A and A in B as a function of temperature. Now point E, where liquidus line meet, it is called eutectic point. Now alloys of the same base metals but with different compositions result in different mechanical properties, and the microstructure of alloy is strongly influenced by the composition of an alloy and the cooling rate during solidification. We will study the microstructure evolution of four alloys in four different regions of the phase diagrams. So firstly, this line is corresponding to composition, which is before there is any formation of eutectic part. So in this case, this is alloy is consisting of 5% of B, and the solidification of this alloy is similar to type 1 alloy. Type 1 alloy meaning it's your similar to isomorphous type of system. So this at T1, your solidification will start. Before this there is completely liquid, then there will be starting of formation of some alpha particles. So alpha will form, and it will form up to this point. There will be complete alpha formation, and the solidification starts by formation of crystals of alpha solid solution extremely rich in A. Now with further cooling, the liquid as well as solid solution, it gets richer in B. So at T4, this point, the remaining liquid will solidify to a alpha phase, and it remains the same down the up to room temperature. So there is not an formation of any beta. Now in case of alloy 2, we are taking eutectic composition. In this case, your 70% B is there, and this is eutectic composition. Your alloy will remain liquid until eutectic point, and at point E, the liquid undergoes a eutectic reaction forming a fine mixture of two solids, alpha and beta. And the reaction is same as that we have seen in type 2. So type 2 alloy was eutectic type of alloy having full solid solubility. Now except that here the liquid transforms into a mixture of two solid solutions instead of two solids. So the composition of alpha phase is given by F, and beta phases is given by G. So with further reduction in temperature, your diffusion in solid takes place in the two phases, resulting in slight variation in composition because your solubilities keep on decreasing with temperature. Yeah.
Ma'am,
Yeah.
by meaning the alpha plus beta phase, actually the both the alpha phase and beta phase combine to form a single phase.
No,
That's like that. And like Fe3 plus alpha means both of these phases are together, and now it is a single phase. Is it like that?
no, it is not single phase. Single phase is only your solid solution or your completely pure solution, or in this case, it is a phase mixture. It is a composite type of structure.
So actually, it is not a homogeneous phase.
No, it's not homogeneous. At micro level, when you'll be seeing, there is, okay, let me show you this type of structure. So there is alpha plates, then beta plates. So this is a composite type of structure. It is a phase mixture. Perlite and eutectic, these are called phase mixture, not single phase. It is just
So
you.
these two phases will be separated using grain boundaries, or they will be single inside a single crystal. I mean,
No,
if we are taking any BCC or FCC structure, the alloying means actually the these other elements will be getting inside that uh, crystal, isn't it? Is it like that?
no, your perlite is a phase mixture. Okay, so this can have a single grain as well. In single grain, your complete perlite can be, but this alpha and beta, which is means Fe3C and alpha, these will be having a physical boundary, phase boundary.
This space boundary means the crystal structure will be different for this alpha and beta.
Yeah, in case of, for example, in case of perlite, your alpha is your Fe3C, which has BCC type of structure, and Fe3C is your orthorhombic type of structure. So this is a different plates of your Fe3C.
Ma'am, by meaning the different structure means there will be different grain boundary between them, isn't it? So,
No,
if we
grain boundary is different. Grain boundary need not to be between these. Your entire perlite can be a single grain as well.
okay, ma'am.
Grain boundary will be having like a different orientation to that grain. So for example, your all these lines of alpha and beta, these are going in this direction. If this direction will be changing, so this is your, these are your grain boundaries, these black lines, these are the grain boundaries. So when your orientation of perlite will change, that will change your grain boundary. These are the grain boundaries. This is your phase mixture of alpha and beta. So it is not a single phase. Single phase is your alpha only, this alpha, or your beta, different separately. Okay, after eutectic, there is alloy 3. In this case, we will be getting some formation of eutectic part. So in alloy 3, there will be 40 weight percent B, which remains liquid until T3. After that, the phase changes are similar to type 2 alloy. So type 2 was your again eutectic type of alloy. At T3, your liquid start to solidify, so there will be formation of alpha. So up to this eutectic line, your alpha will keep on forming. After this, the remaining liquid transforms into eutectic mixture. So here, to solidify crystals of primary alpha, solid solution is very rich in A. So with decrease in temperature, both the liquid and alpha phases, they get richer in B. And when it reaches E, liquid would have eutectic composition, and hence eutectic reaction takes place. After this TE, the alloy will have a primary alpha phase and a eutectic mixture of alpha and beta phases. And the composition of alpha and beta phases will be of the composition appearing at the ends of the eutectic temperature line, which will be F, and at the opposite end it will be G. With further cooling, because of decreased solubility, excess beta will be precipitating, changing the composition. Now, in this case, your structure at the below this eutectic temperature will be almost similar up to room temperature. It will be having pro-eutectic alpha, and remaining will be your eutectic mixture of alpha and beta. Now alloy 4, in this case you'll be see it will be having different type of structure compared to others. So here it will undergo formation of beta without any eutectic reaction. So in this case you are having 15% B which remains liquid until T2. So up to T2 it is liquid, and in this case initially it follows the same process as alloy 1 and its solidification starts at T2. So after this there will be formation of alpha, and here whole alpha will be forming, then below this temperature alpha will be there, and after N there will be formation of beta. So solidification starts at T2 and ends at T5, resulting in homogeneous single phase alpha solid solution. And at M, the solution is unsaturated due to decrease in solubility of B in A. So this is a solvus line. So alpha is showing reduced solubility. So B will come out and form beta. So at N solvus line is hit, the alpha solution is saturated in B, and on further cooling your excess B will come out of solution under slow cooling, and the B does not come up out as a pure B, as A is soluble in B, so it comes out as beta solid solution. And at room temperature your alloy will have mostly alpha with small amount of beta. So this type of structure will be having, so it will give you precipitation type of hardening. Now the small amount of beta will be along grain boundaries, and beta percentage you can measure by using tie line, and if the beta phase is relatively brittle, the alloy will not be very strong or ductile. And the strength of alloy is determined by the constituents of alloy, particularly if the phase is continuous throughout the alloy. And here beta phase is continuous along the grain boundaries. Now these type of curves that we seen, this type of phase diagram which having partial solid solubility and having eutectic reaction, it is seen in lead tin system, and this system is very widely used in making solders. Now because of toxicity of lead, it is now being replaced with other systems. Now in this case these are various types of alloys. So when we are taking the line having very less composition of tin, then this type of microstructure will be seen. So you will be seeing alpha complete alpha. If you move your composition further, then you will be seeing precipitation of your beta, and after this you will be seeing formation of eutectic mixture along with pro-eutectic alpha. So this type of solution is seen in this case, and this is your microstructure that will be seen eutectic mixture and pro-eutectic alpha phase. And in case of eutectic, you will be seeing this type of structure. So these are the eutectic phase which is occurring at the 61.9 weight percent of tin. So at this composition you will be seeing complete eutectic solution in this type of microstructure. And in this case this is your eutectic reaction that is taking place. So your liquid will directly convert into alpha and beta. And why alternating lamellar structure? So because of atomic diffusion of lead and tin only need to occur over short distances. So that's why. So how this microstructure occur? So firstly there will be formation of either beta or alpha, then in the adjacent parts there will be depletion of say lead or tin, so that will be leading to formation of alpha layers. Then again there will be depletion in adjacent part leading to formation of other layers. Now this is how your eutectic will keep growing in particular direction from liquid. Now properties of the eutectic alloy systems. So properties of multi-phase alloy depends on your individual characteristics of the phase. Now how hard your phase is and what is the tensile strength and ductility, this will depend, and how your distribution of phase is in the microstructure. For example, if your eutectic type of mixture is there, if these plates are very small, fine in size, then this will give improved properties. And amount of the phase, how much amount of the phase is present and how many number of phases are present, these all will decide what are the properties of your alloy. And for many commercially important eutectic systems, one phase is relatively weak and plastic and other phase is hard and brittle. For example, in case of aluminium silicon system. Now strength of alloy increases towards eutectic composition as approached from plastic side, and beyond eutectic composition the strength decreases due to increase in size and amount of pro-eutectic brittle phase, and these systems show maximum strength at eutectic composition. Now how to improve their mechanical properties. So mechanical properties can be improved by various methods. By these two methods are used for increasing strength and hardness. First is cold working, other is heat treatment. Now most important heat treatment process for non-ferrous metals is age hardening, and age hardening, it requires a partial solid solubility. Greater the solubility at higher temperature, slope of solvus line, and the above two conditions are true for type 3 alloys, which is lead tin alloys. So as I told earlier, in this type of composition you will be seeing formation of beta, which is forming as precipitation. So this will be showing you age hardening. Now another reaction is eutectoid reaction. This is your simplified iron carbon diagram. In this case, this is your eutectoid point where your solid 1, which is gamma, which is converting into solid 2, which is alpha, and solid 3, which is your cementite. So this is a mixture of alpha and Fe3C. Now a common reaction in solid state where a solid phase transforms into two new solid phases, and the resultant eutectoid mixture is extremely fine, just like eutectic mixture, and it is difficult to find if the mixture is from eutectic reaction or eutectoid reaction under microscope because they look similar. Here in this case, your steel diagram, your this upper line, this is your liquidus, and this below line, it is your solidus line. And eutectic mixture is composed of phases that occur at both ends of eutectic temperature line. So gamma solid solution is here and beta solid solution is in this part. So point aim indicates an allotropic change for pure metal A, and N is your eutectoid point. Other reaction is peritectoid reaction, which is your just opposite of eutectoid reaction. So in that case, your one solid was converting into mixture of two solids. Here two solids will convert into a single solid upon cooling. So it is also a common reaction in solid state. The new phase is usually an intermediate alloy or sometimes a solid solution. Your HP is the peritectoid temperature line. So on cooling, your two solids alpha and beta is converting into gamma. Now these are some other reactions. So we studied about eutectic, eutectoid and peritectoid. Now in case of discussing steel phase diagram, we'll be also studying about peritectic reaction where your liquid plus solid will convert into new solid. And in case of monotactic reaction, your one liquid converts into another liquid plus solid. Now these two liquid will be having different compositions. Now iron carbide equilibrium diagram. So firstly, why this system is so important? So because your steel is by far the most used metal by the industrialized society. This is probably only alloy system that is studied in the greatest detail compared to other systems, and it provides the details understanding the solid state reactions in general. Now this is your cooling curve for your pure iron. When you cool your pure iron at 1538 degrees Celsius, your liquid will convert into delta type of iron, which will be BCC and non-magnetic. After this 1394 degrees Celsius, it will be converting into gamma iron, which will also be non-magnetic and FCC type of structure. After this, it will be converting at 910 degrees Celsius to alpha iron, having non-magnetic properties and BCC structure. At 765 degrees Celsius, it will be converting into magnetic type of alpha iron. Now this is your phase diagram. These are various reactions that takes place. First is eutectoid reaction, other is eutectic point, other is peritectic point. Now Fe3C diagram is not a true equilibrium diagram. Equilibrium implies that phases do not change with time. However, Fe3C decomposes to iron and carbon in form of graphite. This type of decomposition takes place at extremely long time. For instance, at 1300 degree Fahrenheit, it takes several years to form iron and graphite, and hence for practical purposes it can be considered an equilibrium diagram. And this is the iron carbide equilibrium diagram. It is only a portion of the iron carbon equilibrium diagram, so this only goes up to 6.7 weight% of carbon, and in case of iron carbon diagram it will go up to 100% of carbon. Now pure iron upon heating experiences two crystal structure changes. So at room temperature, the stable form called ferrite or alpha iron has BCC structure, and ferrite changes to FCC austenite or gamma iron at 912 degrees Celsius. This austenite persists up to 1394 degrees Celsius, at which FCC austenite reverts back to BCC phase known as delta ferrite, which finally melts at 1538 degrees Celsius. And the crystal structure of Fe3C cementite is an intermetallic compound of orthorhombic type of crystal structure. Now there are various parts of the iron carbon diagram. So in this case it is your Fe3C equilibrium diagram having delta region. In this case it is your, yeah.
Yeah. Ma'am, in the previous diagram, is there any method to connecting this point? I mean, we will be connecting the each for the single phase diagrams, and for two phase diagram, we will be connecting a different temperature to the each reaction line, isn't it? So, is there any method to connecting connecting it? First, we will be joining the single phase region like alpha, gamma, and
Yeah.
um, delta. Then how we will be connecting that other points?
What do you mean? Why you want to connect this to other points?
Not these points. I mean, that 912 degrees Celsius point, and only the 0 and 912 degrees Celsius point is connected to the reaction line, isn't it?
Only 900 is connected to what?
we are having these three invariant point, isn't it? For
Yeah.
the if you take the eutectic point, there is first 0.02, then 0.76 and 6.3. These 912 degree is actually connected to these 2 points, and I mean, is there any order like that, or we are actually deriving this equation directly from the experiments?
Okay, so how we are getting the composition and temperature? That's what you are asking. Invariant points.
Yes, ma'am. But how we are connecting these lines? In one of the lecture, actually, I hear that they are connecting for the alpha regions, and then they are doing it for the two phase region by locating the two single phase region like that.
Okay, so you so earlier, right? 1 second. Let me go back. Okay. Yeah, so this type of cooling curves are present, right? For each composition, for example, 10, 10.2, 10.3, all these composition you'll be getting that percent of steel you took, then you derived this cooling curve. Then you extended this cooling curve to get these lines. These cooling curves are first derived for each composition, then these are derived into these phase diagrams. So like these phase diagrams, you'll be getting, then extending this in terms of this diagram. So like up to this point, you'll be getting a slope, then again in single region, you'll be getting certain slope. Like that you'll be getting. Are you getting my point?
Yes, ma'am.
Yeah, so for that you need to plot the cooling curves for each composition. By using that, these diagrams are derived. So like for example, up to this, only this 0.5% or something, only up to this point you'll be getting this type of reaction. After that, your entire liquid will directly convert into austenite and liquid. It won't be showing any peritectic reaction. That's how they tell like there is no peritectic reaction taking place after this percentage of carbon, and after this percentage of carbon it is converting into this type of alpha and ferrite mixture. Okay. Okay, so now in case of your peritectic reaction, the this is the portion of diagram in the upper left hand corner, and in this region it is called delta region, and here line MP, it is your peritectic reaction line. And from liquid, your liquid plus delta will be converting into austenite, and your maximum solubility of carbon in BCC delta iron is 0.1 weight%. So up to 0.1 weight% carbon is only soluble in delta, and while FCC gamma iron and the solubility is much higher, so point C to be shown later, which will, and the presence of carbon influences the allotropic change. So as the carbon is keep on increasing, so your this line you can see that how delta is converting into austenite. So this line, it depends on carbon percentage. Now NMPB, your this NMPB, the significance of this line, it is shown here. Now on cooling, the line NM represents the beginning of allotropic change from BCC delta iron to FCC gamma iron for alloys less than 0.1% of carbon, and your MP is the beginning of allotropic change through peritectic reaction for alloys between zero point 0.1 to 0.18% of carbon. NP will be your NP will be end of allotropic change. So up to here your complete change will take place. PB is your beginning and end of allotropic change by peritectic reaction for alloys between 0.18% carbon to 0.5% of carbon, and at PB allotropic change happens at constant temperature. alloys with more than 0.5% of carbon, it solidifies to austenite directly. There won't be allotropic change or delta solid solution or peritectic reaction. And the delta region is of no engineering interest as the phase is unstable at room temperature. Other is eutectic region. It is after this uh, 2.1 weight% of carbon. If it is present there, then this will be cast iron, and there in these cast irons your eutectic reaction takes place. Now at eutectic point your carbon percentage is 4.3 weight% and your temperature is 1147 degrees Celsius. Here and at eutectoid point your zero point 0.8 weight% of carbon and 727 degrees Celsius is your eutectoid temperature. Now CED, this is your solidus line. It is also eutectic line where your liquid iron transforms to eutectic mixture of austenite, gamma iron and your cementite Fe3C, and the mixture is called ledeburite, and the above eutectic mixture is not seen in the microstructure. Now at room temperature when we see steels, you want to be seeing this eutectic mixture because your austenite, which is part of your ledeburite, is not stable at room temperature. Now this austenite which is formed here, this austenite will further convert into ferrite plus cementite. There will be formation of this eutectoid reaction. Now small solid solution area is left to line GH, and at 912 degrees Celsius the change of crystal structure of pure iron from FCC gamma to BCC alpha, and the above area is portion of small amount of carbon dissolved in BCC alpha iron called this ferrite region. Now up to 2.1, up to this percent is your steel, and after this is your cast iron. And hypoeutectoid and hypereutectoid, will study about this as well. So in eutectic region HJK, this HJK is your eutectoid line, where is your austenite which is formed after eutectic reaction. It will transform to eutectoid mixture of ferrite and cementite called pearlite. These pearlitic steels are used in drawing ropes, piano strings and suspension bridges, steel cords for tire reinforcement, etc. And pearlite is very strong bulk material, and any austenite present in the solution should transform to eutectoid mixture of ferrite and cementite. Below eutectoid temperature line, every alloy will consist of a mixture of ferrite and cementite, and your steel composition is less than 2% of carbon. Cast iron is between 2 to 6.67% of carbon. Eutectoid region. Now in this case, cooling of an alloy with eutectoid composition, which is 0.8% of carbon, at A your microstructure will be fully gamma iron. So after this, gamma is your austenite is here. After this your austenite will convert into, start forming in at eutectoid composition, it will directly convert into complete pearlite. So the gamma phase undergoes an allotropic transformation due to the eutectoid reaction line and transforms to a fine microstructure of alpha iron and Fe3C. So this is lamellar type of structure where you will be seeing Fe3C lamellae alternating to your alpha, and the fine microstructure is called your pearlite. This is your reaction. Your 0.8% carbon will be converting into 0.025 weight% carbon known as ferrite plus cementite having 6.7 weight% carbon. Now these are relative layer thickness of ferrite, alpha and cementite in pearlite is 8 to 1. Now, if the width of ferrite is 8, then your Fe3C will be 1. Now, mechanically, perlite has properties between soft ductile ferrite and hard brittle cementite. And the phase transformation requires a redistribution of carbon by diffusion. So, similarly to eutectic type of transformation, firstly, your cementite layer forms. Now, in the adjacent area, there will be depletion of carbon leading to formation of ferrite. Then again, there will be excess of carbon leading to formation of cementite layers. Now, this is how your growth of perlite will take place by assisted by carbon diffusion. This is your microstructure of complete eutectoid steel showing complete perlite. In this case, your black portion is your cementite and white portion is shown as your ferrite. In case of hypoeutectoid steel, it will be having lesser carbon than eutectoid composition. So, for example, here it's taken 0.3 weight% of carbon. So, let us go through cooling of a hypoeutectoid alloy having 0.3% of carbon. At C, it is your complete austenitic structure. After you go into this two-phase region, then there will be formation of alpha particles. So at C, the alloy has gamma phase and until it touches the line MO. At point D, the system is in two-phase region, alpha and gamma. Most alpha particles form along the grain boundaries of gamma, so they form at grain boundaries. And composition of alpha and gamma phases is determined by the tie line. So you can make a tie line and get the percentage of carbon, and using that you can find out percentage. At D, your D point, the alpha consists of 0.02% of carbon and gamma consists of 0.4% of carbon. Now after you move below this point, so with further cooling, your weight percentage of alpha is increasing and gamma is decreasing. It can be seen here. So alpha is keep on forming. You can also see this by if you keep on forming tie lines, then also by calculating you can find out that your amount of your alpha will keep on increasing. The alpha phase gets slightly richer in carbon along Mn, while the change in composition of gamma is more along MO. Now cooling from D to E results in increased fraction of alpha phase. At this point, alpha phase has 0.025% of carbon and gamma phase has 0.8% of carbon. And with further cooling just below eutectoid line at F, all the gamma phase will be transforming into perlite and remaining will be your proeutectoid alpha. Now there is virtually no change in already formed ferrite, and the eutectoid reaction results in transformation of 37% gamma phase to a fine eutectoid mixture of ferrite and cementite, which is called perlite. This is your perlite phase and remaining is your proeutectoid ferrite. Now at the eutectoid line, your austenite is an interstitial solid solution with each grain dissolving 0.8% of carbon in FCC iron. Now ferrite, however, is BCC iron dissolving very little carbon. So change in the crystal structure cannot occur until the additional carbon comes out of the solution. So the first step is the precipitation of carbon atoms to form plates of cementite. In the area next to cementite, the iron is depleted of carbon, hence they can form PCC alpha iron ferrite immediately. Now if you have amount of carbon higher than 0.8% carbon, then your steel will be hypereutectoid. So in this case, you're cooling off a hypereutectoid alloy at 1.1 weight% of carbon. At G, this is your complete austenitic structure. After this, when you reach at H, there will be formation of cementite at grain boundaries. Now, at G, the alloy is in single phase FCC gamma iron. When it touches the line PO, it enters two phase region gamma Fe3C. And just below PO at H, your particles of Fe3C start appearing along the gamma grain boundaries. And your line PO, this line PO, it is indicates the maximum amount of carbon solubility, so solubility will decrease with reducing this temperature. So the solubility of carbon at H is lower than G, so excess carbon will go and form cementite. So excess carbon comes out of gamma and forms cementite along gamma grain boundaries. And just above point I, this point I, your cementite will be 5.08% and remaining is gamma phase. When it hits the eutectoid line, remaining gamma iron transforms to eutectoid reaction forming perlite, and at the eutectoid line all the 95% of gamma phase it undergoes an allotropic change of FCC austenite to BCC ferrite. As the in case of hypoeutectoid alloys, remaining austenite having 0.8% of carbon would form a laminar type of eutectoid mixture of perlite, and line PO involves only a change of carbon solubility, whereas the horizontal line, this horizontal line, it refers to the allotropic change. Now this is your microstructure of hypereutectoid steel, where this proeutectoid cementite network forms at the grain boundaries and which is surrounds the perlite grains. Effects on mechanical properties. Now ferrite is soft and has a medium tensile strength, 275 MPa. Cementite is hard with low tensile strength up to 34 MPa, and combination of both of these two phases in eutectoid composition as perlite, it produces an alloy with much higher tensile strength around 827 MPa, and the amount of perlite increases with an increase in carbon percentage for a hypoeutectoid steel. Hence, the tensile strength and Brenner hardness increases up to eutectoid composition 0.8% carbon, and your ductility and impact strength always decreases with increase in carbon content. And beyond eutectoid composition, your strength levels off or sometimes shows a decrease due to brittle cementite network. And your Brinell hardness, it continues to increase due to formation of cementite network. That's all from my side. Now if you have any query, you can ask. If you have any query, you can ask, or you can leave the meeting if you want.
Ma'am,
Yeah.
in the wrought iron, actually, when we talk about the slag, actually, we'll be removing the slag, isn't it? So, why we are mixing the slag with that in the wrought iron?
And the wrought iron. Slag,
Yes,
slag you mix to remove some impurities, right?
yes. The
So
flux and slag will be mixing to remove it. We will be removing it, isn't it? The impurities will be density will be lower, and we'll be removing it, isn't it?
yeah, so that's the reason you're adding that. So to remove the impurities, if you are removing more impurities such as sulfur and different impurities, that will make your steel better properties compared to your having higher impurities.
But in the wrought iron, are we mixing it for any getting any properties?
Slag. Slag.
Let me. I will read that sentence.
You are not adding. Yeah, are you there? It is not added intentionally. Intentionally, it's like the manufacturing process that you use. So to deoxidize your ore, so for that you need to add slag. So this is like byproduct. It is not like you are not making it
Ma'am, I will read out the thing. It's actually what they are saying is during rolling, the slag particles will get elongated in the direction of rolling, which increases the strength. It is actually given for the
okay.
wrought iron.
Wrought iron, you are rolling it, then it is elongating your particles, so it is increasing your strength of material.
Yes, ma'am. Also, they are also saying like during the forging or hammering,
Yeah.
it is actually mixing it with.
Okay. So okay, if your it is consist of some sulfide particles or like that, then it can make your material brittle. But otherwise, if it is like some silicates or some your ceramic particles, then it might increase your strength of material as well because of like precipitation hardening type of effect. What is it? Is this question in this assignment? This
No, ma'am. Actually, while reading the wrought iron, it's actually they are saying that it is called the wrought iron since they are saying like during the forging, the slag will be combining it with
okay.
it's actually given in the region of your wrought iron. It's
Okay. So that's why its name is originated. Okay. That may be a reason. In metallurgy, you mainly study about wrought iron when you contrast like wrought iron versus cast iron. So cast iron is you made by casting your iron, and there'll be a lot of impurities. So that acts as very brittle material. But when you talk about wrought iron, then in that case you'll be having very less percentage of carbon. So it is ductile compared to your cast iron. So that may be that is the only part I'm aware of. I'm not aware of like how the processing works, why they are adding slag.
And also the Gibbs energy, actually the Gibbs energy should be negative for the formation of the phase.
Yeah, it should reduce if you want to go forward in reaction. If it's like equilibrium reaction, if you want to go forward, then it should your Gibbs free energy should reduce from the previous your product for reactants.
Ma'am, also for that density equation in the unit cell, actually we are using the Avogadro number in the denominator, isn't it? Is there any reason for adding the Avogadro number in the denominator? I mean, for the in the density equation, we are, the equation is actually given by Nz by Vc into Na. Actually, the density is actually mass by volume, isn't it? So N is Z is actually the weight of the atom, and N is the number of atoms inside the unit cell.
So,
So if
no, the weight
we,
that you are using it is molecular weight, right? So there it is already considering Avogadro number. So that's why you need to divide it because you're considering like four atoms, right? When you're getting the density of unit cell.
so we don't need to so we are using the Avogadro number denominator for that. The N is
Yeah.
actually taken at the top numerator, since the number of atoms in the unit cell is 4.
Yeah, you're talking in terms of atoms, right? When you are getting your unit cell number of atoms, so that's why, and you're using molecular weight, not exact weight, like how much iron you are using. Like it is not in 2 kg, right?
Yes, ma'am. We will be taking the Z by Na as one term for getting the single weight.
Yeah.
Okay. Ma'am, by meaning the Gibbs energy, actually there was statement like a crystal structure always has more free energy than the non-crystalline structure. So if the free energy, I mean, by meaning the stable means we will be having less energy, isn't it? So why it is said like a crystalline structure always have more free energy than the non-crystalline structure?
No,
Crystalline
crystalline
structure is more.
crystalline structure has less energy. Like they are negative and gives free energy. Amorphous structures will require higher energy. They are metastable systems, your amorphous structures. So if you leave, like for example, your nanocrystalline materials or your amorphous materials, if you leave them for very long time, they will try to convert into crystalline structures. Because in case of crystalline structures, you know that they are your equilibrium distance and all that you have studied, right? Equilibrium distance will be followed at a unit particular unit cell. They are sitting, your atoms are sitting, there is an equilibrium distance. So this all will make your system more energy favorable. So a material is more likely to go, if you are like solidifying your material very slowly, then it is more likely to solidify in terms of crystalline structure, which is more stable. And if you are using non equilibrium processes, such as you are cooling it very fast, then it is more likely to go and form an amorphous type of structure, because you are not providing that much of time to solidify it in terms of a very stable structure. So you are providing extra energy from outside during manufacturing.
The statement is actually wrong. Is a crystalline structure always has more free energy than a non-crystalline structure? Is that correct? Um,
More free energy, like it.
the statement is actually a crystalline structure always has more free energy than a non-crystalline structure.
Crystalline.
They are actually comparing with the polymers and structures of that polymers and solidification. Like
Gives free energy. Gives free energy should be lower, right? For crystalline
yes,
structure.
yes, actually, the for negative free energy, that means it's more stable. But they are actually given for the definition of the crystalline material. They are actually giving one point like this: a crystalline structure will always have more free energy than a non-crystalline structure. So I was just confused why actually both of them are contradicting, isn't it?
More free energy. It depends on how you define like have more free energy. If you're talking like in terms of, if you're talking taking mode of this, like it can be more negative, right? More negative, then it will be more stable. So you need to check that online. I'll see whether if I can find crystalline structure free energy. It's given in notes or in some assignment.
It's actually from a textbook. I mean, I think I will post that image in the forum, so you can get the full picture of that.
Yeah.
So,
Yeah.
ma'am, also during that phase transformation diagram, actually, do we need to when we are increasing the cooling rate, the order is actually given in the diagram. Like first, it will be coarse perlite and fine bainite and featherly bainite and coarse bainite. So actually, why this coarse bainite is coming at the bottom? It should be at the top, isn't it? The When we go more steeper, then the microstructure should be increasing, isn't it?
Okay. You are starting from above. So first you are getting coarse perlite, then fine perlite, right?
Yes.
Then coarse bainite,
Then featherly bainite, coarse. Then they are written coarse bainite.
then below that
Below that, they have given two lines like Mart stage start and Mart stage MS and M
MS
final.
and
Uh,
MF, yeah. Finish, start and finish, yeah. So,
yes,
so above coarse benite, what is there? Feathery benite.
featherly bainite. Yes.
Coarse benite.
If we consider
Okay.
the coarse and fine, actually it should be
Ben benite is
about
told in terms of upper and lower benite. Like it will be, it has like different morphology, like they are needle type of and platelets type of. So that is, I don't think it's given in terms of coarse and feathery. I have heard, but not coarse benite. It will be in next chapter, right? For heat treatment.
yes, yes,
Okay, so but sir has already posted the lectures, right? For
yes.
heat
I think
treatment. Okay. Okay, I can check that in next week.
Okay. And one more thing is actually when we are increasing the too much speed, it's actually coming steeper, and it will be missing that two lines, isn't it? I mean there will be two lines for starting and ending, so it will be forming the amorphous form. Will it be
In
forming
which
in
case?
the TS diagram? I mean phase transformation diagram. If it misses there is a two C curve, isn't it?
Yeah.
So if it misses the first C curve starting curve, it will be it will be
It
in the
will,
form of super cold liquid form.
yeah, then it will convert into your Martensite, right? MS and MF. It will directly go to MS. So,
But in order to form the martensite, it should be crossing that first C curve, isn't it?
no, C, if it is
Yeah.
going into C curve, your cooling curve, then it will be forming your perlite or benite. If it is going into that C curve, if it is directly going without touching those curves, then it will be forming like 100% martensite, or it will also be forming like some retained austenite. If it won't be forming like 100% martensite in that case.
So, by meaning the super cool liquid, it's actually martensite. So it don't need to necessary to cross that C.
Super cool is your, yeah, can you repeat?
A super cool liquid state.
Is your, no, it can be martensite, can also be retained austenite, like some percentage of retained austenite, so it might not change as well if your MS is not approaching.
Ma'am, does that mean the super cool means the it's like glass forming similar to that amorphous form, isn't it? So, does that mean the martensite has a
No,
don't have a particular order, but I
no,
mean it's actually
martensite is metallic. It won't be like glass like, it will be metallic structure, it will be, but it will be having very high density of defects. It has high number of dislocations, it has high number of twins, so that gives it like different properties compared to your pearlitic structure. It won't be like metallic glass here, because that metallic glass requires a lot of high cooling rates compared to your martensitic.
okay. Ma'am, by meaning the hardening, is it chart from the after the yield point or to the fracture point, or is it from the elastic from the zero to yield point hardening?
Hardening.
I mean strain hardening. Is it after the yield point to the fracture point, or before the to till the ultimate point? By
See,
meaning the strain
strain
hardening.
hardening, when we tell strain hardening, then it is your accumulation of dislocations and interaction. So it starts after yield point. Okay, up to yield point, it is only elastic type of deformation. So after that, it will start your strain deformation, strain hardening. It occurs up to your fracture point. But when you tell like in terms of your engineering graph, then up to UTS, you show that it is taking place in strain hardening, but it is occurring in entire region. But your cross section is reducing, so that's why your curve comes down. But strain hardening is taking place in entire region.
So we will be considering for engineering viewpoint. We will be mainly focusing on from yield point to the ultimate point.
UTS, yeah. When you like try to balance why it's coming down, then you tell like it's losing its cross section. So they are trying to balance. Strain hardening is occurring in entire region up to fracture point.
Okay. And also the elastic modulus actually higher for the um, carbon fiber or the metals. If you consider take an order of carbon fiber, steel.
metals and polymers and ceramics, then in what order will the carbon fiber come? I mean, it will be
Okay.
greater than all of this, or it will be in between.
This question is not in assignments which are due, right?
No, it's actually in another exam. The this question was actually got.
Okay. So when you talk about elastic modulus, so it is telling you like how hard it is to deform an elastic region. So it is very high in case of ceramics, and carbon
Yes.
fibers also have very high elastic modulus. So it's between ceramic or your carbon fiber. So you need to check what is the answer.
Okay, we can actually place it between ceramic and metals.
Yeah, metals have less elastic modulus compared to ceramics and your carbon fibers. Carbon fiber is also acts as your ceramic, right? It is also brittle. It will have similar your fracture curve, your uh, engineering strain curve similar to ceramics.
Okay, ma'am, does that mean the higher elastic modulus? Does that mean it is having more elasticity?
Elast it doesn't have high elasticity. It resists elastic deformation in your elastic region.
Okay.
Like if you are applying a particular amount of your strain stress for the both metal and ceramic, then your metal will deform more compared to your ceramic at the same stress.
Okay. Thank you, ma'am. So can I leave? I
Yeah,
have no more doubts.
yeah, you can leave.
Thank you, ma'am.